Let's examine the table that's included in your PowerPoint slides handout, IR Spectroscopy. The title is Structural Units and Absorption Frequencies. This table lists the average frequencies in wave numbers for commonly encountered bonds in organic compounds. The listing gives the highest frequencies at the top, with frequency values decreasing from top to bottom. Note as well that because stretching frequencies tend to be higher than bending frequencies, we see that for the most part, stretching frequencies are given in the upper half of the table, while bending frequencies are listed largely in the lower half. Note at the very bottom, the CO stretch is at a very low frequency, relatively speaking, so it's a bit of an exception to the rule. All right, let's look at some of the specific bond entries. We'll start at the top. An alkyl CH has an average stretching frequency and wave numbers of 2800 to 3000 reciprocal centimeters. Now remember this value 3000, it's important. If we examine the stretching frequency of an alkynyl CH, we note that it's at a higher frequency, from 3000 to 3100. So this frequency value, 3000, is kind of a dividing line. CH stretches that belong to the alkane family will occur at values below 3000. Alkynyl CHs will have frequencies that are higher than 3000. And one reason for that is an alkynyl CH is a tighter bond than an alkyl CH. Generally speaking, the tighter the bond, the higher the frequency. If we look at the third entry here, this is an alkynyl CH. Well, the alkynyl CH is even a tighter bond than the double. Therefore, not surprisingly, the frequency of this alkynyl CH is even higher than the alkynyl CH. It has an average of about 3300 wave numbers. The next entry is the hydroxyl group, as found in alcohols and phenols. This is the OH stretching frequency. Now, generally speaking, the average for the OH stretch is about 3500 wave numbers. This table shows that there can be variation, and indeed there can be. Hydrogen bonding will tend to lower the observed frequency. And one other thing to note, that if we are talking about the actual peak signal for an infrared spectrum corresponding to absorption by the OH stretching frequency, that one thing to pay attention to is, well, two things: the size of the peak and the broadness. Typically, an OH peak in the IR spectrum is broad. They're some of the broadest peaks that we will see among all the peaks. Now, next entry is carboxylic acid. Note this, the values listed here, 2500 to 33,000. That's not just a range within which a narrow band falls, but rather that is the average width of the OH peak, the OH stretching peak in the infrared spectrum. Now that is extremely broad, and this is the broadest peak that you will find among all possible peaks in IR spectrum. In fact, I like to refer to it as the camel's hump in the IR spectrum, because it's very characteristic that looking for that camel's hump can help you to identify a carboxylic acid when you have it. just remember then, the OH of a carboxylic acid is very broad, on average stretching from, well, a high of 3,300, and that can vary all the way down to 2,500. The next entry in the table is an NH peak. Now an NH peak, in terms of the frequency value, is very close to the OH peak. Can vary in range from 3,300 to 3,500. Now the NH peak is also somewhat broad, but note this, that the NH peak is not as broad as an OH peak. And that's one way we can distinguish between amines and alcohols. Next entry in the table is the Carbonyl Ch of an aldehyde. In the IR spectrum, there are typically two peaks to look for. That is, the stretching motion here produces what's called a doublet. There are actually two stretching frequencies that are both there. And in the if you had a sample of an aldehyde producing the IR spectrum, you would look for and see these two peaks, 2720 and 2820 reciprocal centimeters. And that's very characteristic of the CH stretch of an aldehyde. Those two peaks, some people call it a doublet, 2720, 2820. Next we come in the table to the CC double bond stretch of alkenes, and related to that is the CC stretch of an aromatic compound. Alkenes and aromatic compounds are related. In fact, let's go back up to the entry for alkenes. I forgot to mention that this entry has two functional groups, alkenes and aromatics, because the CH stretch for both of them occurs in the same place, 3,000 to 3,100. If you have an IR spectrum and you see a peak between 3,000 and 3,100, you couldn't immediately say whether it was an alkene or aromatic. Both are possible, so you have to look deeper, have to look further in to tell. Now, one way to tell that is to look at the CC double bond stretch in your spectrum. There is a similarity difference between the frequencies of the CC double bond stretch for alkene and the CC stretch for an aromatic compound. The CC stretch of an alkene is a peak in the region from 1600 to 1680 wave numbers. For aromatic compound, it's in a similar location, but a little different. There are actually two bands we tend to see, two peaks, around 1500 and around 1600. Now, kind of remember that these two peak values, 1500, 1600, tend to be indicative that you have an aromatic compound, and it's caused by this CC stretch in the aromatic ring. Well, the next entry is a CC triple bond stretch. It is found between 2100 and 2270. Now, before we go further, one thing to note, you can compare a bit. Compare the CC triple bond stretch with the CC double bond stretch of an alkene. You can see that the CC triple bond stretch of the alkyne is a higher frequency than the CC double bond stretch. And that makes sense because the triple bond is a tighter bond than a double, and as I indicated before, the tighter the bond, the higher the frequency. Now that raises the question, what would the frequency of a CC single bond be? Well, it's certainly going to be less than, say, 1600. And though it doesn't list it in this table, it's around 1,000, the CC single bond stretch. It's a looser bond, lower frequency than a CC double stretch. Right. Next entry we come to the Carbonyl C double bond O stretch. The average stretching frequency from 1680 to 1740. Now this one's very important because if you have a carbonyl group of an aldehyde ketone or ester or some other functional groups, the peak that's produced by that stretch is one of the biggest in the entire spectrum. It's very prominent. It's not all that broad, it's somewhat narrow, but very big peak. And you find it at a characteristic region. There isn't much else in this region from 1680 to 1740. Now this carbonyl stretch for different functional groups, and there's a lot that are possible, can be a little lower or a little higher than 1680, or lower than 1680 or a little higher than 1740. Next we come to a carbon-nitrogen triple bond stretch. We're all still in the stretching bonds. That's called the nitrile group, and the average stretching frequency of the nitrile, this carbon-nitrogen triple bond, is around 2220 to 2260. Now we start to enter the bending modes, bending frequencies. Now I'm not going to go through very many of the values at this point. The reason is, if you look at the values in the table, the regions are generally very broad, and there's lots and lots of overlapping with all the different functional groups. Now that makes it difficult to say get an IR spectrum, interpret it by looking at the frequency values on the right side of the spectrum, namely due to the bends. There's so much overlap. The regions where they occur are so broad, it's extremely difficult, in fact I'd say impossible, to determine the functional group based just on examining frequencies in the bending region. So one thing to point out at this juncture is that when you're interpreting an IR spectrum, you want to focus on interpreting the left half of the spectrum where your stretching bands are, and completely ignore, at least at the beginning, completely ignore the bending bands, because they're too difficult to make a correlation between a given stretching frequency and a possible bond or functional group. So when you're interpreting an IR spectrum, and we're going to review this later on, stay with the left half. Your task is to use the stretching frequencies to try to identify what functional groups are in your molecule, and to stay away, at least initially, from making that kind of interpretation from the bending peaks. Don't even examine them, at least at first. Now, later in our discussion, we'll point out that, in fact, stretching bands do have meaning, and they can give you some additional information about structure, but we'll talk about that a bit later.